Hello, welcome to all. This is the second part of the discussion of particle in a 1D box. We have to discuss a few more points and one problem as an example. That's all. It requires 10 to 15 minutes only. Okay, we have already solved the Schrodinger equation for one-dimensional box, particle in a one-dimensional box, and we have obtained the expression for energy, etc. The wave function for particle in a 1D box is psi equals square root of 2 by L sine n pi x by L, where L is the length of the 1D box. N is what we call quantum number, which can have value 1, 2, 3, etc. And if we plot this psi versus x for different quantum numbers, n equals 1, the plot will look like this. 0 to L we are plotting. So psi value initially when x equals 0 is 0. That is the wall of the vessel, wall of the box. Then it increases as x increases, reaches a maximum at midpoint where x is L by 2. X corresponds as L by 2, midpoint of the box. Then decreases and becomes 0 when x becomes equal to L. That is the other wall of the box. That is fine. Then we take the wave function for n equals 2. There we can find two humps. Initially, the wave function increases, attains a maximum, then decreases, becomes 0 again. That happens at the midpoint, that is L by 2. Then it decreases, the value becomes negative. It becomes more negative, reaches the most negative value or maximum negative value, and then decreases to 0 at x equals L. That is it. So we have at the midpoint, psi becomes equal to 0. On LHS, psi is taken as positive, and RHS, the psi is taken as negative. The positive and negative signs for psi doesn't signify much. We can leave as such. Now we can come to probability distribution for a particle in a box when n equals 1 and n equals 2. Probability means the square of wave function. Square of wave function represents probability, that we know. And the curve is somewhat like psi curve itself. For n equals 1, the probability increases at and reaches maximum at midpoint, then decreases to 0. Okay, at the midpoint we have maximum probability. But for n equals 2, we see that psi square value increases, reaches a maximum at L by 4, 1/4 of the length, then decreases to 0 at L by 2 or the midpoint, then again increases to another maximum at 3 by 4 L, then decreases to 0 at L. That is it. So we have two maximum points, one at L by 4 and the other at 3 by 4 L. And we have a 0 in between two regions of high probability at L equals 2 or midpoint of the box. And such a point we call it as node. So here we have a node. For n equals 2 we have a node. And we can see that in the psi function curve, this is the psi square curve. In the psi function curve, node is the point at which psi is also 0, but at the two sides of that node, we will have psi function positive and negative. So positive value of psi decreases to 0 and then becomes negative. Psi is continuously changing. That is it. and we can have nodes when n increases. So when n is equal to 3, we will have 3 bumps of particle probabilities, and we will have 2 nodes. When it is 4, we will have 4 bumps and 3 nodes. So in general, we will have n minus 1 nodes. We can see that the probability changes with increasing energy of the particle and depends on position in the box. So the probability depends on 2 factors. Energy, that depends on quantum number we have already seen. When quantum number increases, energy changes. Okay, that's fine. We compare the probability curves for n equals 1 and n is equal to 2. You take the midpoint. We compare the same point. We can see that for n equals 1, the probability is maximum, but for n is equal to 2, the probability is 0 at the midpoint. So we can see that it depends on the energy in a position. We are fixing the position and finding the probability for different quantum numbers corresponding to different discrete values of energy. So that will depend on the quantum number or the energy. As it changes, the probability at a point also changes. Now you can take a particular quantum number, particle is having a particular energy. You take n equals 1. Energy is the same, but when you change the position, the probability changes. It increases, reaches maximum, and then again decreases to 0 for n equals 1. For n is equal to 2, increases at a maximum point, reaches a maximum point, then decreases to 0, again increases, reaches the second maximum, and then decreases to 0 again. This result is different from classical physics. If we have a particle in a box, it can be 1D box, and it is obeying Newtonian equations, the probability of finding the particle will be independent of the energy and same at all points in the box. If it is moving with a uniform velocity, we can imagine the probability will be the same. It's rebounding at the wall, just like a Newtonian particle. Okay. This is psi curve for 3 different quantum numbers. N equals 1, n is equal to 2. We have 2 bumps here and a nodal point, a node here. Here we have 3 regions and we have 2 nodal points for n is equal to 3. Okay, now we can come to the energy state as well. N equals 1, we have already seen the energy is En equals n square h square by 8 ml square. For n is equal to 1, it is h square by 8 ml square. For n equals 1, it is h square by 8 ml square. N is equal to 2, it will be 4h square by 8 ml square. N is equal to 3, it is 9h square by 8 ml square. N is equal to 4, it will be 16h square by 8 ml square. It is not 7, it is 16h square by 8 ml square. There is a correction in the diagram. Okay, that's fine. Now we can take the difference between 2 consecutive levels. N is equal to 1 and n is equal to 2. The difference is 3h square by 8 ml square. N is equal to 2 and n is equal to 3 level. The difference is 5h square by 8 ml square. N is equal to 3 and n is equal to 4. It is 16 minus 9, that is 7h square by 8 ml square. So what happens? The difference between 2 consecutive levels increases as we move up in the quantum ladder. That is, we increase the quantum number. The energy increases and the difference between the 2 consecutive levels also increases. That is it. That is the nature of 1D box. So if it is a free particle in the absence of confine, we are not confining the particle between 2 walls. The particle is free. Then we can see that energy will be a continuum. There is no quantization of energy. equals 1, the energy is given as h square by 8 ml square. That corresponds to what we call the ground state. We can compare the waves with what we call the standing waves in a violin string. There is a close analogy. These are the psi square curves for different quantum numbers. This is psi 1, that is n equals 1, psi 2, that is n is equal to 2, this is psi 20, that is n equals 20, wave corresponding to that. Now we can consider a problem and find the solution in two different manners. One is the analytical method, where we use the equation and do the mathematics and find the answer. The other one is using the diagrams we have already seen and getting qualitative inferences which are as good as the quantitative treatment. Our question is, for a particle in a one-dimensional box of length L, the second excited state of wave function n is equal to 3 is. The wave function is given as psi equals 3 square root of 2 by L sine 3 pi x by L. So we put the value of n here, n as 3, then you get this wave function. Okay, we are asked to find two parameters. What is the probability that the particle is in the left half of the box? Okay, fine, that is the length between L by 2 to L. Sorry, length between 0 to L by 2. That is the left half. The other one is right half, that is L by 2 to L. So we are asked to find out the probability in the left half. Similarly, one more parameter we have to evaluate. What is the probability that the particle is in the middle third of the box? We divide the box into 0 to L by 3, L by 3 to L into 2 by 3 L, L into 2 by 3 L, then 2 by 3 L to L. Okay. We can do the analytical method. The solution can be simple integration. We have to integrate psi square dx between the points required. So we arbitrarily fix the points as A and B. We have to find the probability between the region A and B. A and B can be any points in the 1D box. So probability from A to B will be integral A to B of psi square dx. And for psi square we have to put the psi 3. That is psi 3 equals square root of 2 by L sine 3 pi x by L. And when we put that, probability becomes, we are squaring the function. So 2 by L integral of A to B sine square 3 pi x by L dx. That is a standard form of integration of sine square function. We can simply integrate it. We get this function, probability function P AB equals 2 by L x by 2 minus L sine 6 pi x by L divided by 12 pi between limits A and B. Okay, when we apply limit, we can simplify it as B minus A by L minus 1 by 6 pi sine 6 pi B by L minus sine 6 pi A by L. So that is our integral for the probability between 2 points A and B. Okay. Now we can, what we can do, put the value for A and B into this expression. So first part of the question is find the left half of the probability in the left half of the box. Left half means distance from 0 to L by 2. So A is put as 0 and B is put as L by 2. We put the values there and do the simplification. We get probability as 1 by 2. Okay. Then we can find the probability in the middle 1/3. In the middle 1/3 as well. What we can do, A is put as equal to L by 3 and B is put as 2 by 3L. And put the values here and do the simplification. And we get P as 1 by 3. So final result is quite simple and okay in this case. This we can infer by simply looking into the probability diagram here. For n equals 3, it looks like this. We have 3 bumps of equal size and equal length. You can see that first bump is from 0 to L by 3, the second is from L by 3 to 2 by 3L, and the third is from 2 by 3L to L. That's fine. If you take L by 2, we can see that on the left hand we have a 1.5 bumps, and on right hand side also the same. And the integral psi square dx should be equal to area of the graph, area of the curve. So we can see that area at the midpoint will be 1.5 hump here, 1.5 here, they will be of equal area. So what will be the integral? Integral will be 1 by 2. Probability will be 1 by 2. Half of the total area. If total area is taken as 1, half of the total area, that is 1 by 2. And you take the middle 1/3. 3 humps of equal size, middle 1/3 have 1 hump. So what does it indicate? It indicates in the middle 1/3 of the box, we have a probability 1 by 3. That is it. So by simply looking at the probability picture, we can get the probability between given points. But it is not always possible. Suppose we are asked to middle 1/3 of this psi equals 1, then we will have to do the integration. And this is a psi function. Psi function will have standard integrals as well. We can use that. That is another thing. Okay, that's fine. Now, you can look at the energy diagram here. You take the ground level energy as E1, that is 1 unit. That is h square by 8 ml square. That is E1. This will be, second will be 4 times E1. Third will be 9 times E1. Fourth will be 16 times E1. Fifth will be 25 times E1. Where E1 is the energy of the ground level, that is h square by 8 ml square. So we can substitute that there to find the energy of different quantum numbers, different energy levels. And we can also see from the diagram the difference between two consecutive levels increases as we move up the ladder. One more question. For the particle of one-dimensional box, the ground state wave function is psi 1 equals square root of 2 by L pi x by L. Right? What is the probability that the particle is in the left half of the box in the ground state? You can do the integration as the above and put the value of A and B there as 0 and L by 2 and find the value. If you find the value, it will be 1 by 2. You can look at this graph. It reaches maximum and come to 0. It is what we call a normal distribution graph, and so half of the box will correspond to half of the area traced by the curve as well. So it will be 1 by 2. For that matter, any quantum level, half of the box means probability is half. Let the quantum number value be anything. That is it. For n equals 2, also the same is true. And it will be, you can see that every quarter of the box, the probability will be the same for n is equal to 2. N is equal to 4 also, that will be true. Okay, that is it. So this type of problems we can expect. And if we have this graph in mind, we can simply put the solution within a second, within a few seconds itself. We need not go through the integration. In some cases, we will have to go through the integration itself. Okay, that's all. Thank you. We will meet again with the 3D box, particle in a 3D box. Thank you. Bye.